children. Today, you're going to learn about linkages by Bree Belaski and Janelle Oliver.
What the heck is a linkage? A linkage is defined as a set of rigid bars or links which are connected by rotational joints. In general, we consider planar linkages, where links only move in parallel planes. A linkage also has lower pairs. There are 3 different kinds: turning pairs, prismatic pairs, and higher pairs. A complete linkage contains an even number of bars connected in a way that allows 1 degree of freedom of motion. A linkage can be formed using any amount of even number of bars, but not odd numbers. If a linkage has odd numbers, that means the fixed bar has joints on it that became pivots, turning the linkage into an object called a link work. A link work consists of an odd number of bars that pivot at 2 points to a fixed plane. 2 pivot points, yes, okay. A linkage configuration is a description of the positions of each link at a particular moment in time. Typically, at least one of these links within the configuration are fixed in place, as the others move around it. These structures are also known as mechanisms. This fixed link makes it possible for the moving links around it to construct algebraic curves and straight lines. With a constant or variable velocity ratio, linkages can be used to convert these 3 things: continuous rotation into continuous rotation into oscillation or reciprocation, or oscillation into oscillation or reciprocation into reciprocation. Now we're going to talk about the types of linkages.
Okay, so the first type of linkage is the crank and slider linkage. A crank and slider linkage is a type of 4-link mechanism with 3 revolute joints and 1 joint that slides. The crank rotates, causing the slider to move in a line. Due to this, they can move in many paths. Next is the reverse motion linkage. The top and bottom rods move in opposite directions. So, as the top rod moves to the left, the bottom rod moves to the right. The center of rotation comes from the fixed pivot. Next is the parallel motion linkage. All of the rods are parallel. The bottom small rods move in one direction, while the large top bar moves in the other direction. And lastly, we have the bell crank linkage. This type of linkage allows for horizontal and vertical movement. An example of this is brakes on a bike. Some other types of linkages are the Watt linkage and the Poisselier-Lipkin linkages, which are 2 prime examples that we will look into later on.
So how the heck do we know this stuff? The origin of linkages begins with James Watt, this man right here, a Scottish engineer who discovered the concept while working on the steam engine. This concept of rectilinear motion, or motion in a straight line or lines, was sought after in an attempt to find a more convenient way of communicating the motion in the steam engine's piston rods to the angular motion of the working beam. Watt patented this idea of parallel motion and gave us the standard explanation of a simple 3-bar linkage. AB and CD, being 2 equal radii revolving on centers BC, and connected together by rod AD and moving together through arcs of certain lengths, the variations from the straight line would be nearly equal and opposite, and that the point E would describe a curve nearly straight, and from this construction afterward, called the parallel motion, was derived. Initially, it was thought there was no way to create perfectly rectilinear motion using linkages. That was until L. Lipkin, a freshman at the University of St. Petersburg, and Lieutenant
Poisselier,
a young French officer of engineers, created the Poisselier-Lipkin linkage. This link consists of 7 bars. 2 are long and of equal length that both pivot to the same point. The other extremities are pivoted to opposite angles of a rhombus, made of 4 shorter equal lengths. These 6 links create what is known as the post-ciliary cell. The 7th extra link is made to move so that the free end of the rhombus creates an accurately straight line. Some functions of linkages are function generation, which is relative to motion between the links connected to the frame, path generation, which is the path of a tracer point, and 3, motion generation, which is the motion of the coupler link. And this is an example of Watt's curve, and this is the polar equation that describes it. This is the post-ciliary Lipkin linkage and how it creates a straight line. Okay, so now we're going to do, now we're going to do a demonstration. Due to our lack of supplies, we're doing a very simple version of Watt's linkage and creating a straight line. So, you start off with 3 pieces of whatever that are the same length, and then you take one of them, cut them in half, and that's your middle piece. Okay. So you take your thumbtacks and you put them so that you connect your little piece to your big piece, like that. Okay. Then you take your pen or whatever the heck you've chosen to use. You stick it in there. Okay. Need assistance in holding the things down. Okay. Like that. Okay. So basically these are your pivot points and these are your fixed points. Janelle's hands. Yes, okay, great. Now I'm gonna attempt to do a straight line. Keep in mind this is cardboard and not great. Okay. Yeah, okay, stand still. There. Okay. Wow, I love when pens don't work. Please hold. Okay. Okay. That's a straight line. Woo!